Hi, everyone. Welcome back to the seminar room. Second seminar in 2 days, so that's absolutely fantastic for everyone here and on Zoom. So it's a pleasure for me to welcome Isabel Rebollido, who started her career as a PhD student at the Universidad Autónoma, working here in the cab. Well, not physically in this cab, in the other cab at ISAT, where she worked with Iva Villaver and Benjamin Montesinos. And after her PhD, you moved to the US, right? To the Space Telescope Science Institute in Baltimore, where Isabel was a postdoc there for 3 years. And then after that, she was awarded a Juan de la Cierva Fellowship, which brought her back to the cab here in Spain. And since January 2024, Isabel has been a sort of prestigious ESA fellow, where she's been involved, or is currently heavily involved in JWST and CHAOPS, and she's going to talk to us today about Beta Pic. I think I pronounced that right. CHAOPS, is that how you say that?
That's how I say it.
That's good.
Hopefully it's okay.
So yeah, I'll let you take it away, Isabel.
Great. Thank you so much, Lee, and thank you, Laura. Thanks for inviting me and for organizing. This is such a nice room and setup for a talk. Okay, so the title of the talk is A Comprehensive View of the Beta Pictoris System. If you are not astrophysicist, Beta Pictoris might not sound familiar to you. And if you're an astrophysicist and you don't work in small scale stuff, it might still sound not familiar. But it's a very important system for the people who study from planets to planet formation, etc., because it has it all. And I'll try to convince you that it's interesting and that it has it all, and that if you're interested in planet formation, you should look at it. So let's start from the beginning. And the beginning of not only Beta Pictoris, but the beginning of basically all studies of planet formation comes in the 80s with the infrared astronomy. And this is an image. This is the first image we have of a planetary system. And this is the system Beta Pictoris. And it is not casual that Beta Pictoris was the first system to be imaged, because it's a very young star, so it's still bright, and the disk is bright. It is really close. It's only like 19 parsecs. Most of the planetary systems that we know that have significant amounts of material in their disk are farther out. And it's really bright in the infrared. It's a disk that is really, really bright. We measure the brightness of our disks with the infrared luminosity with respect to the luminosity of the star. And like 10 to the minus 3 might not sound to like a lot, but most of these we deal with are 10 to the minus 5, so a couple of order of magnitudes lower. So what you're seeing here in this image from 1984, this was taken in Chile, I can't remember exactly the telescope now, has what we call a coronagraph, that it's a physical element that goes in the telescope that blocks the light of the star. And that's what allows us to see what's accompanying the star, that it's this material that it's really bright, again 10 to the minus 3 with respect to the brightness of the star, and that's dust. It's just dust. That's the only thing we see, and it's dust that is reflecting the light of the star at these wavelength ranges. But we can also see how the dust thermally emits at different wavelengths. So what is this dust and where does it come from? It's not the same dust as the dust in protoplanetary disks. The dust in protoplanetary disks, you can see here an example. It's much more extended and it's much more dense, so it's optically thick. The light can barely go through it. And also these disks, these protoplanetary disks that form just after the star starts to radiate, are also very gas-rich, and they're really, really massive. But as the planet formation process goes on, a lot of this material is lost. It's lost either to the interstellar medium, with a lot of material being just blown away by the radiation of the star, or being accreted onto the star, or being accreted into larger particles. So protoplanets, for example. And we usually get this carving of the disks, where we have a lack of material in some of the parts, and you create rings or belts. And like ALMA has provided a lot of images that show these structures in a variety of systems. So we're only now starting to learn how these disks and rings form and so on. But how debris disks were differentiated from protoplanetary disks at the beginning were just through photometry. And we would construct these spectral energy distributions that you can see here that show just the flux against the wavelength. So for different wavelengths, we would get different brightness levels. And basically, we would just get like a gap here. So there is, in the mid infrared and near infrared, they were much less bright than protoplanetary disks that were super bright, or like a star that is just, it doesn't have any material around it, right? You can see here for comparison as well. So these are disks, the debris disks that Beta Pic is, or these young planetary systems, have depleted a lot of the initial material, have started to form planets, and have carved gaps and belts and rings in the material. So this is what we see when we look at these disks with the telescopes, but this is more or less what they are actually like. So you have a young star in the center that it's already a main sequence star. So it's already burning hydrogen and some helium, and it has all of this material around it, that it's basically the leftovers of the planet formation. You're starting to create some agglomerates of dust and creating rocks and stuff like that. So protoplanets, but these rocks collide. They are not just like doing their own thing. This is dense enough that there's collisions that produce material that causes other collisions because it collides with itself. So that's what we call a collisional cascade. And that's what generates the dust that we see in debris disks. This, of course, lies out with time. So at some point, we will stop seeing the dust. And we will have a system like our solar system where we do have some asteroids, comets, etc. And we have some dust, but it's mostly dust depleted as well. So these disks are called debris disks, and differently to the protoplanetary disk, are optically thin, so the light actually goes through them, and have a bunch of material like something that I'm really interested in, that it's exocomets. So like comets in the solar system, there are small rocks that evaporate. Well, they exist as well in debris disks. There are actually people who call them exocometary disks. So I told you these disks are gas depleted, but they're actually not. They were, on the classical planet formation theories, they were always talked about disks with no gas. But the more we look into them, the more gas we actually find. And this was not a thing until the advent of ALMA and SMA, and like these all submillimetric arrays that allows us to see molecules, like CO is the main molecule we see in debris disks. But we have actually been seeing gas in debris disks for 40 years. Just after this image was taken in 1984, spectroscopic observations of Beta Pic and other systems, it was not the only system, but this was one of the most conspicuous ones, showed this, showed these tiny absorptions here that are not coming from the star. This is the calcium line, the calcium 2 line, which a lot of people that work on stars will know. And this is the line that comes from the photosphere of the star. These stars rotate quite fast, so the lines are broadened. So what is this peak? This can't come from the star because it would also be rotationally broadened. This comes from the disk. So since 1985, we actually know that there is gas in this system. And not much later than that, and actually the same team, there are still some people that were PhDs at the time that are working on this. Now, not much later than this, they found that there are actually variable features of the gas. Do we have a stable gas component that is just a disk of gas around the star? But the gas also can vary. You see for different light styles here in the legend, there are different dates, and creates different features that are, in this case, they are all redshifted, so to the right. And those features are the exocomets in the system. Those are bodies that have ices, that have dust, that go really close to a star, and they evaporate. And you can tell me, but Isa, you just said this is calcium. Yes, we are so close to the star at this point that the calcium sublimates. And it not only sublimates, but ionizes into calcium 2. So we can see it. But we do see other elements on exocomets. We don't see the volatiles but we see other refractory elements like iron, silicates, magnesium in the ultraviolet. So the advent of Hubble even showed us more exocomets in the star. And you can say, okay, this is 87. Did people follow up? Do we know any more exocomets at Beta Pic? Yes. This is a plot from, this is a video from, I don't know, 2014 or 13 or something like that. And this is how many exocomets we were seeing. Check the dates. Here, they don't change very much. I think it's a couple of years. This is how many exocomets we see. And you can see here how the spectra just changes. And we see all those tails of bodies that are crossing in front of the star. And this is just, here it shows the average in red and all the comets we see in all the different spectra in black, showing all the comets. So yeah, we know lots and lots of comets in Beta Pic. We think the system is kind of something like this. It's being bombarded constantly by exocomets or bodies that are evaporating. You can call them however you like. Actually, fun anecdote, they discovered this in 87. First planet around solar type star was 92. So exocomets before exoplanets, these absolutely did not fly with the community. So these exocomets were first called falling evaporating bodies. Because, yeah. So yeah, this is what we think we have in our system. Our star here in the center, we have a lot of dust that is being created from these collisions between these small bodies, and then a lot of material that is approaching the star and evaporating. And we know so many exocomets in Beta Pic. You can say like, okay, so what do you know about the exocomets? Well, we know that there are at least 2 different families of exocomets in Beta Pic. And this is just based on statistical studies. We had to use, well, they used a lot of models. I was barely starting my career in science in 2014. They used a lot of models to extract the information from basically the radial velocity and the depth, because that's everything we could measure. And they discovered that they were like basically 2 different families that you could split in radial velocities, and the full width maximum, that it's basically the width of the absorptions, and the absorption depth. So they knew that there are comets coming from different regions of the system. And I don't know if this sounds familiar to anyone, but that's exactly what happens in the solar system. We have 2 main family comets, which are like the long period comets and the short period comets. Ones are coming from the inner regions of the solar system, and the other ones come from much outer regions. So this is a very similar case in just a random planetary system that just happens to be really bright and really close, so we can observe it very well. And with the proper orientation, because if we had an orientation that it's face on instead of edge on, we wouldn't see the comets transiting, so we wouldn't see this. Okay. And this is all in a spectroscopy, but with the advent of exoplanets and exoplanetary studies, there were a set of missions that appeared. The first one, I think it was Corot, or it was the first big one for me, but then it was Kepler. That might sound a bit more familiar to you. Now we have TESS, we have Cheops, we have Plato coming up really soon. And we started to look at the light curves as well. And if we see the comets in a spectroscopy, wouldn't we also see them in photometry? And we do. But note, this is 2019. Since 1985 that we started looking at exocomets, they had to pass like almost 40 years, 30 years to actually see the comets in photometry. And you can say like, wait, what do you know that's a comet? Well, these features that we see in photometry, they're not periodic, so we cannot really follow them. So a lot of people might argue that it's a different thing, but explanations are welcome. It doesn't seem to come from the star. And it also, for the small ones, it's really hard to tell. But for the big ones, we have a very particular shape that it's depends, a sawtooth, sharp fin. Different people have their own favorite analog. But what we see, it's a sharp ingress that is the head of the comet starting to pass in front of the star. And that's like a solid body or a round body, sort of like, that could also be the coma. So comets have a coma and then a tail. But then the egress, it's an exponential decay. And that's just the tail that it gets fainter and fainter and smaller. So yeah, that's why whenever we see this shape, we're like, wait, great, an exocomet. So we see thousands of exocomets in spectroscopy. You saw that in just a few days on that video, there were so many. But we don't see that many in photometry because we don't really know yet. We don't know if we need the exocomets to be further out to see them in photometry. We don't know if they sublimate so much that the ones that are really close to the star, we don't really get to see them. But we see enough that we can make some statistics with them. And this is another really nice paper from 2022, where they also use models to create statistics out of the exocomet population in Beta Pic. This is, remember, I'm still talking about the same system. And what they do is show the radius of the comet and the cumulative distribution. And you can see roughly that it follows a decaying tendency. And that's, well, the fit, like you could argue that doesn't really fit the points, but I think that's just to guide the eye. And what it's trying to guide you to is the fact that the distribution of comets in the solar system is actually very similar to the distribution of comet sizes in Beta Pic, which is something, if they put this plot to you and you're like, yeah, of course, because the formation mechanism is probably similar, right? You're just aggregating stuff into the same thing. And it's probably similarly efficient, etc. But this was not obvious until we saw this. So we are always talking about planet formation based on what we know from the solar system, because it's the only system that we really can study like in all its parts. But we never had proof that there are actually like big similarities for small bodies, which is crucial because you need the small bodies to create the big ones. So yeah, I really like this paper. Okay, enough about exocomets. All these exocomets live somewhere. They live in the disk. And the disk is extremely complex. And the more we look at this disk, the more stuff we see. One of the first things that we noticed of the disk when Hubble was up and we were able to study the disk from space and with high sensitivity is that, yeah, the disk is really nice. It's like really flat, edge on. This is, again, a chronographic mask that blocks the star. But it's not only that disk, like there is like a secondary thing. And they spent a few years not calling this a secondary disk, but calling it a warp, because it's kind of hard to disentangle whether this is like a different element or it's just, I cannot do it very well with the cursor, but you can see that there is sort of a warp there. Yeah, so why is there warp? Like where is the warp coming from? And or a secondary disk. And you see that there is like plenty of studies. I'm not very good with the cursor, but yeah, there's plenty of papers from the 90s and the 2000s that were studying these very same phenomena. And it's not the only weird thing that we see in the disk. We have plenty of wavelengths. This is a paper from 2015 that it's fantastic. And we have plenty of wavelengths where we have looked at the disk, and everywhere we see weird stuff. You can see the warp here, maybe a little bit here in the NACO, in the K-band. If we go to the mid-infrared, then it's just like bonkers. It's like we have like a blob here, and that it shows kind of like in ALMA as well, but further out. And we know that we have a clump of gas. This is gas. All of these images are dust, except for the last one. So it's like, okay, the disk is not only composed maybe of two components that are inclined with respect to each other, but they're also clumpy. So there is a lot of stuff going on in this disk. Again, we can only study this because the disk is so bright and so close. So this was puzzling people for a long time. And you can see it better here in the paper that actually reported this publication by Bill Dent. This is the first detection of CO gas in a debris disk. Again, at a point where everybody thought the debris disk didn't have any gas, even though we knew from the 80s that at least some gas was there. But we didn't expect certainly any molecules. And it is clearly non-symmetrical. And moreover, the gas disk that, if I could do a straight line, you can follow here, is not really at the same inclination as the dust disk, sort of like inclined. So let me recap, because this is a lot of things, right? So we have a disk that shows like maybe two components or what, that shows gas, that the gas is also inclined, that shows a lot of clumps, even in the gas. So there is so many things going on in this system. Everything, I will try to like make a nice picture of all of it, but let me introduce another couple of things first. It just gets more and more complicated before you can start to solve it. The disk also has planets. The first giant planet was discovered through direct imaging. This is a composite image of NACO. So here's the disk. Here is the coronagraphic mask that it's blocking the star for the disk image. And here is a smaller coronagraphic mask that it's blocking the star for the planet image. And here's the planet. And we know very well the orbit of the planet. This was discovered like almost 20 years ago. We have imaged more times this planet, and we can see it, like you can Google it. There are images of this. There are GIFs and videos of the planet moving around. And the planet, it's in a kind of weird orbit. It also seems to align better with the secondary disk than with the main disk. And this was just like perfect, because a lot of people were saying, like, how do you get a secondary disk that it's inclined? Well, if you have a planet that it's inclined, then you can disrupt material and like make it basically chase the planet and create the secondary disk. Yeah, first thing explained, great. And then second planet appears. I was like, damn it, what do we do with another planet now? So the second planet is even inner to Beta Pictoris b. It's closer to the star. You can see this is the same composite image showing just basically where they are located with respect to the disk, but the disk goes almost all the way in. We don't, because the disk is edge on, it's really hard to say like where the cavity ends. But we know there is a cavity. Yeah, so are they maybe like creating a scenario like this? Are Beta Pictoris B and C responsible of the shape of the disk? Yeah, so that is another, let's say, piece to the puzzle. I think I've introduced all the weird things in Beta Pic, and I'm gonna talk now about my contribution to this system. Let me recap. We have exocomets. We have a disk. We have a secondary disk. We have clumps. We have clumps in the gas, and we have two planets. I know it's a lot, but trust me, it all makes sense in the end. Okay, so obviously what we did once James Webb was up in the sky was point to this system. We know it has everything, and we're super interested in what goes on with the system, so we need to look at it with James Webb. It did absolutely not disappoint. This is what you get just from the imaging mask. That is the archive. It's like the first reduction that Space Telescope gives to you, like, here you are, this is the data. And you can already see that the disk is really bright. In the mid-infrared, this is 23 microns. Here's the disk. And you're like, okay, cool, this is the main disk. What is this? Is this real? Is it not real? Well, you see again the coronagraphic mask. We're blocking the star. Okay, so we started to play with this. We knew that there was going to be a lot of artifacts because coronagraphs might seem very useful. You just block the light of the star and you see the planetary system, but they create a lot of optical artifacts, but they are really tricky to subtract. And the PSF subtraction in James Webb, it's obviously optimized to deal with imaging, but not with the coronagraphs. So that's something that the team that I was on worked in a lot. They actually developed this tool that it's online and it's free, that it's called Space Clip. And then for the specific Beta Pic case, we created this MC RDI by Kellen Lawson that also works very well. And he also used it in AUMIC. If you know about disks, you know about AUMIC as well. So this is what we got with a different stripe. So this is how it looks like. You can see a couple of things right off the bat from this image. First, that it's two images. I don't know if you can see one here, and the other one is kind of, I'm doing this really badly. Like one goes this way, and the other one goes that way. And we have the mask here, and then we have these two spikes that come just from the bar. The bar, it's like a solid bar, but when you combine the two different images that we took with two different rolling angles, it creates that spike. But we can see the disk pretty well. I hope you can see the disk pretty well with the slides. And we're starting to see something weird here. Or like, damn it, that's just an artifact. How do we get rid of it? This is so weird. And then we worked on deconvolution from the PSF. So you deconvolve the PSF. But again, it's a really complex PSF because of the chronographic mask. And that thing doesn't go away. I was like, what is going on? Because we knew there was an inclined disk. We were not supposed to find inclined disks, but we were not expecting like weird stuff going on here. There's something weird going on with the images. There's something weird going on with the chronograph. What's happening? We then took the two images. These are the two images combined, and we looked at them separately. There are definitely the different images are going to show us what's in the plane of the telescope, not the plane of the sky. So if this is an artifact, if this is something that's wrong with the telescope or whatever, it's going to show in the rolls. But then when we compare the rolls, that's still there. So there is still something weird going on. And it's not only that that survives. It's not only this weird spike that survives. It's all of these. So we have a lot of stuff, again, going on in the disk. We kind of knew, we thought we kind of knew what was going on with the disk, with the planets, with the disk, blah, blah, blah. The planets maybe are creating the secondary disk, whatever. And then suddenly we get that. And it gets better because in the other wavelength that we had two different filters, we also see it. It's still there. And all this weird stuff is still there. By the way, there are two different coronagraphs. There are different coronagraphs in James Webb, and we use two different ones. That's why the images look different. And you can also see that the deconvolution here, it's much less nice than for this coronagraph. But yeah, it works. Okay, so weird stuff that we're seeing. Here's our secondary disk. We kind of knew we were going to find this. I hope you can more or less see it with the contrast. But we knew we were going to find that, but we didn't know we were going to find this. So we immediately, because we're astronomers, we called it the cat's tail because, yeah, why not? So now everybody calls it the cat's tail. So I guess that's cool. And you can actually combine the two filters and see, they did this really beautiful image in Space Telescope. There was actually a press release with NASA, with ESA. CAB also had a press release with it. And you can see how some of the features immediately pop up. Like the secondary disk, maybe with this blue line, you don't see very well, but it's, we call it extended secondary disk because it gets further out than in previous images from the ones from Hubble, for example. We have the main disk, and then we have the cat's tail, and this thing that we call the nebulosity. And you can say immediately that there are different colors in different areas of the disk, and that means that the compositions are probably slightly different. Okay, what happened here? What is the explanation we give to the fact that we have a cat's tail in Beta Pic? We call it a dust production event because we don't want to say collision, because we don't have proof that it was actually a collision. So what we think is that there was a dust production event somewhere close to the star, here on a point, let's say here, and different material was created from that collision. And that material, all dust, has a property that we call the beta value, this beta. And depending on that beta, we would have different trajectories of the material. Beta is just the ratio between the radiation force from the star and the gravitational force from the star. So if the gravitational force is higher, then the orbits are going to be, or the material is going to be constrained in an orbit around the star. But if the radiation pressure is higher for that particle, then it's going to be blown out, right? Either in hyperbolas or anomalous hyperbola. So what we think happened is that we have here a dust production event. Some of the material is staying, and it's creating this extended secondary disk. And some of the material is being blown out, and it's creating the cat's tail. Yeah. And because this is a dust production event, and you have like kind of a hotspot of production of dust there, you had many cat's tails. And those many cat's tails are the nebulosity that we are seeing in the background. So we believe that this is something that happened time over time over time, like just we keep creating collisions there or dust production events, and material is being thrown out of the system. And because we have colors, we have some colors. Well, let's stay with the beta. So with the beta value, knowing that this is material that it's unbound, so the top part of the plot, we can already constrain more or less what type of material we're going to have based on like if it's silicates or organics or carbon, and if it has vacuum or it's just like very dense, compact, either porous or compact. And we know that the grain size is going to be around like 20 microns or so because we, with the wavelength roughly, the wavelength at which we took the images roughly correlates with the size of the dust that we are seeing in those images. So if we're around here, we are more or less confident that the material has a lot of vacuum, but it might still be either organic or silicates or something like that. But because we have a couple of colors, then we can look at the SED and compare the spectral energy distribution, see the fluxes, and compare what's the ratio. So basically, what's the color of the material we are seeing. And the color kind of tells us, we think, that is mostly organic material and that is very porous, which is something that we also find in comets in the solar system. So it's not a crazy composition. Yeah, and so we favor, and you can see this, all of this in the paper, much better explained, which longer explanation. And we more or less favor a composition where we have a lot of organics, mostly organics, and then a lot of vacuum. But yeah, so we have a video that Space Telescope also made, and this is what we thought happened. The orange disk is the main disk. The bluish disk is the secondary extended disk. This is the star. And I think it's going to happen somewhere here, the collision. So pay attention to that way we can play it again. Up there. So that's the dust production event. The dust is expanding back. It's leaving the system. That depends on the rotation of the system. So we had to assume a rotation direction. And because there is an optical effect, then it creates this shape. You want me to play it again? Yep. Good to see that you are at least awake. There you go. Material leaves the system, and once you turn to the inclination that we actually have, you got the cat stay. So yeah, so we're here. And you can say, but Isa, you said so many things about the exocomets, the secondary disk, the clumps, the gas, blah, blah, blah. What happens if I put one of those plots, the gas one, for example, although it could be other one, on top of this? Well, that happens. The dust production event seems to line up with the location of the gas in the disk. And the initial explanation for that clump of gas was that there had been a collision 150 years ago. And that lines up exactly with the creation of our cat's tail. We could have a collision there 150 years ago. And based on the material that we can assume from the colors and the fluxes, that material would have gone further enough to create the shape of the cat's tail as we see it now. But the cat's tail should still be progressing, should be moving, should be evolving. So what we want to do now, and what we have done, is take images again of the cat's tail and see if we can actually see it move. To be fair, I think it was a prediction of like 1 to 2 pixels. So it's going to be tricky to detect, and it's going to be trickier to convince people that we're actually seeing that. But we're on it. And I can say a couple more things about this disk because well, I worked on the cat's tail, but I'm also part of the team that worked on the medium MRS spectra. We not only pointed James Webb with the coronagraphs, but we also used the spectrographs, the integral field spectrographs. And so they discovered a really interesting thing, that it's if you take the data we have now from James Webb and you compare it to Spitzer, and you make just like an extraction, like if you had the Spitzer angular resolution. So you're basically comparing apples to apples. You're comparing the spectra from Spitzer to the spectra from James Webb on the same location. Boom. It's completely different. Like this system has gone to hell. Half of the features that we loved from Spitzer, that they were like, wow, silicates in Beta Pic, this is so cool, from, 20 years ago, are gone. And not only that, but the flux in the inner regions has completely decreased. So we might also have had a collision 20 years ago or so that created all these features in the inner regions. This is much closer to the star than where we see the collision that created the cat's tail. Like we say in collision, but it's dust production of that. We might have had another one. So what this is telling us is that this system is incredibly active. There's so many things going on. There's probably planets, terrestrial planets forming right now in this system. Yeah, and we can also see that from the mid-infrared, from the images, from the clumps that we see, there is a debate going on whether those clumps have moved or not, whether they are part of planets that are being formed right now, or whether they are part of the collision. And yeah, I think I have it on another slide, but there is so many papers going on about this and whether we can tell if this has moved or not, because we don't have consistent data. We have data from so many different telescopes. But of course, when you're comparing data from one telescope to another, there is a slight systematic error. So we cannot be certain yet, but we are still trying to put all of these clumps together with the whole story. And to complicate things more, we're finding argon-2. Argon-2, like argon is being ionized in Beta Pic, and we don't really know why. We're at a point where we think this star, that it's an A-type star, has a corona. A-type stars should not have coronas. Like this comes from the convective zone. A stars should not have convective zones. So you could say, what's going on with this? Like, we don't really know. We try to see if it was from the interstellar medium, from the star, we don't know. We don't really know. So yeah, hopefully the new data that we have will give us some more explanations on actually this detection. And it's not just like a pixel that kind of shows the argon. It's extended. It's spatially extended. You can see here the planet. So it's significantly extended. But yeah, talking about the planet, we also have NIRCam images. And NIRCam is another instrument in James Webb that goes to slightly shorter wavelengths. This is near infrared. And we do see stuff in these images. So here it looks kind of mild. This is just a disk. Then all the artifacts, like all these little dots, most of them are just coming from the subtraction of the PSF and the artifacts from the telescope. But we wanted to see Beta Pic. And according to predictions, the detection limits were lower, so we should be able to detect Beta Pic. This is solar system planets for comparison, and Beta Pic is up here, like it's really close to the star, and it's really, really bright. So where's the planet? There. So we see the planet Beta Pic B with NIRCam. We also see C. No, we don't. C is way too close. And because we're using a coronagraph, we're losing a lot of basically physical size because of the instrument, because of the physical part of the coronagraph that blocks the light. But yeah, we do see B. We have kind of awful astrometry though. So we're basically not able to tell anything more about the orbit. One of the explanations for this really not great astrometry in Beta Pic was discussed that maybe Beta Pic was a binary. So we kind of freaked out because we've been studying this star for 40 years. It cannot be a binary now. We cannot just add more things to the system and complicate it even more. But this is honestly something that we're still looking into. It would be extremely rare, but who knows at this point. But we could take the data from NIRCam and try to constrain better the atmosphere of Beta Pic. We already had a lot of data from gravity. Like this data is incredibly precise for measuring exoplanet atmospheres. And we also had GPI, which is not as precise, but it's also really nice. So we put the James Webb data in, and truth is, it doesn't really say that much more than we already knew. But yeah, we have a couple more wavelengths that we can add. But because we also see it with the spectrograph, remember I told you it was there in the argon image, we can also take the spectra, we can also take the spectra of the planet, you can see here, and also like the disk. It was kind of complicated actually to subtract the disk component from the planet, because you basically have to go to the other side here, measure the disk, and then subtract it here. But we know the disk is not exactly symmetrical, so it was kind of tough to do this analysis. But we can get the spectra from MIRI and add it to this plot. So now we have a much longer wavelength range, and it did help a little bit to constrain the composition of Beta Pic B. So yeah, with this new data, we're doing a lot of things. There is still a lot going on, and you see that there is still a lot of open questions, but yeah, we're trying to solve them little by little, and we're getting new James Webb data. It's past 45, so I'm gonna bring up the summary and the conclusions. So I hope you agree with me that Beta Pic is a very complex, very interesting system. We still don't know if exocomets are connected to collisions. So we know that there are a lot of exocomets since at least 40 years ago. We know there was a collision 20 years ago and another one 150 years ago, and who knows how many more that we have not tracked. But we don't know if comets are linked to that. The actual standing explanation is that they're actually being disrupted from their orbits by the planets. So the planets are throwing the comets in. Yeah, we have discovered a nice fork and the cat's tail. We don't have any new planets from the NIRCam images. We have like decent limits, but no new giant planets find. Yeah, NIRCam was, to be fair, compared to MIRI, a little bit boring. Like we have really nice data, but not as exciting. And yeah, getting the photometry of the planet is really hard because the disk is a contaminant. So even though it's a bright planet that it's close by, that we can observe, that we know a lot about its orbit, we cannot really tell a lot about its atmosphere with precision because just the disk is not helping. We don't even know if the disk is being accreted onto the planet, if some of the material of the disk is contaminating the atmosphere of the planet. We already have the data for that program. Marcel Perrin was my supervisor when I was in Baltimore, and he took MIRI MRS again, but focused on the cat's tail region. So we basically have the data of the spectrograph from that region. We will hopefully be able to see the composition of the cat's tail and if it has moved or not. So whether we had a good hypothesis or a bad hypothesis. And I also want to let you know that there is a paper coming out by Sarah Betty, who is a postdoc now at Space Telescope, with really exciting results about the composition of the disk from also spectroscopic data. And I think I'm going to leave it here. And thank you all for coming and listening to me.
Fantastic. Thank you very much, Isabel. That's an absolutely fascinating seminar, I thought. So yeah, really kind of fascinating to hear how in depth you sort of understand this other, solar system, I guess. But yeah, fascinating. So questions?
Hi, very nice talk. So I have a couple of questions. The first one is about the dust production event.
Mm-hmm.
So what do you think is the region that produced this increase in the production of dust, and why the dust that was produced by this event is flowing away, making this cat's tail, and is not staying there?
Yeah, so wait, I'll try to get my mouse back. I don't think I can. Here, sorry. I'm going back to this line. Yeah, okay. So we say dust production event because we don't have any proof that it's actually a collision, but we think it was a collision. We think it was two bodies that just collided and destroyed and generated a lot of dust. How do you make two bodies collide in this system? Well, we have two disks. we think one of the disks is actually connected to the planet because it's in an inclined orbit. And the material in that inclined disk, it's interacting with the material in the main disk. And so if you have two large bodies, you could have thrown the material in the orbit of the secondary disk, creating the extended secondary disk. So some of the material, it's actually bound to the star. But other material has been created with a different property. Maybe it was like smaller dust or more porous dust that it's more affected by radiation. So the material that it's more affected by radiation will not stay bound to the system. It will go out in elliptical orbits, or sorry, in hyperbolic orbits, which is what's happening with the material in the cat's tail. And the rest of the material that it's less affected by the radiation of the star is not being blown out. It's staying bound, and it's in this.
Okay, and do you have any idea about the size of these bodies?
So roughly, the dust that we see is correlated with the wavelength that we are observing at. So we're talking micron-sized dust. That's more
of the two bodies. The bodies that,
that
yeah. Collide.
We do have a rough mass estimate, but it is really tricky because we only have two wavelengths. So it's hard to tell how much dust was actually produced. So we can only see the dust that was produced at these wavelengths. We don't see these in any other wavelengths. So I think we were talking like a few Ceres masses. But yeah, it was a very rough approximation that actually the referee of the paper asked for because we didn't want to do it. And the referee asked for it. So we said, okay, we'll pretend we know what we're talking about.
Okay, thank you. And the other question was about the beginning of the presentation.
Yep.
I was wondering, when you show these absorption lines of exocomets that are not symmetrical. So my question was about how can you distinguish between an exocomet and an exoplanet using these kind of things? You mentioned the periodicity and also the shape of the tail.
Yeah.
But what about if you have an exoplanet that is being photoevaporated as well?
Yeah. So if you have a planet that it's being photoevaporated, it has to be really close. So it will have a very short period. So you should be able to see it multiple times.
So you combine both evidence?
Yeah.
Okay.
So the thing with it also would create, I would assume, a much deeper absorption, like the transit, let's say. But yeah, these things we have not seen any of these absorptions or transits that is periodic or that we can associate to something periodic.
Okay, but if it's produced by the comet, in principle, could be also periodic, right?
Sure, but the periods of comets are much larger. So, okay. So this is a bit tricky because when we say comet, people immediately think of comets in the solar system. And this is a debate going on in the field. And yeah, the exocomet field is very small, but we are still some people. And the only agreement that we have reached is that exocomets are things that evaporate. We don't really know where they come from in the system, even though we think come from the outer regions, because otherwise they would not. We think that the orbits wouldn't be such that we see so many of them evaporating, but we don't really know where they come from. We don't really know what's their composition, and we are barely starting to know their sizes. So whether you have a small body like a comet or a large body like a planet evaporating, it is really tricky to distinguish. And it would be, for us, I think it would basically be the periodicity. A planet, you would have a periodicity that you can follow. Comets, we expect them to have much larger periods, so we would just not see them. Like if you have a planet evaporating close to a star, it has to be really close to a star, and that you will see.
Okay, thank you.
Okay, thank you. Got another question here.
Thank you. The talk was really interesting.
Thanks.
So thanks for that. My two questions are very quick. I'll try to be quick. So just the first one is just to recap, if I understood well, this secondary disk is not exclusively produced by the dust production event, right? It's because of the eccentricity of the planet, but it has been fed by the dust from the event.
Right. So you need the secondary disk in order to have a collision that would be the dust production event that we see afterwards.
Okay.
So the secondary disk has to be there before, and we think the planet is driving it.
Okay, thank you. And my first question goes back to the very beginning where you mentioned that planet formation theory doesn't predict gas at those stages of the protoplanetary disk. And it was, and there is gas probably because of the comets and the exocomets, but the disk is Beta Pictoris is quite young. It's like, and so I wonder if, because I'm not in the field, I imagine photoevaporation just acts very quickly, because I know that in a disk, there is a dust and a gas fraction. So I guess 20 million years is already too long for photoevaporation?
Yeah, that's a fantastic question. So the early works, I'm not a protoplanetary disk person, let's say that first of all.
Me neither.
But the first papers that would talk about the lifespan of disks would deal with protoplanetary disks, which are like the disks that are first formed when you form the star, the material that stays around it. And they were supposed to last around 12 million years.
How long?
12 or
Okay.
15.
Mhm.
But this is dependent on the spectral type. Larger stars dissipate their disks faster because the radiation is higher. So for example, it is really tricky to find disks around O or B type stars. Actually, B type stars, we know very few disks, but O type stars, I don't think we know any disks around them because the radiation is just so high. So these are A type stars. Well, Beta Pic is an A type star, and A type stars don't have such a strong radiation field as B and O, but the radiation field is still much stronger than, for example, a G, like our sun. So the disk should be depleted from most of the material fairly quickly. But there is a few systems around the A-type stars where it's being debated whether they are debris disks or protoplanetary disks based mostly on their gas content. So classically, what we use to distinguish between them is what you see in this plot. It's the spectral energy distribution. So if we have the near infrared range at the level of the photosphere of the star, we would say that the disk is no longer protoplanetary. Classically, I think it was called class 3, but for the ones that also have the mid-infrared kind of depleted, we already call them debris disks. Debris disks are brighter in the far infrared. So when you have depleted so much of the dust and your disk is no longer optically thick, the gas should be depleted as well, because the gas would be depleted faster than the dust. Okay, what happens now is that we keep finding gas in debris disks. And the community keeps debating whether that gas is of primary origin, so it's a leftover from the protoplanetary disk, or of secondary origin. So it's being created through collisions, like the collisional cascades that produce the dust, exocomet evaporation, or giant collisions even between protoplanets or whatever. So the fact that we thought gas was not present in debris disks and now is, has created a debate within the field. And we're still, like, people are still talking about it. We are trying desperately to find hydrogen or not find hydrogen to a sensitivity limit where we can say, okay, like this cannot be primordial because hydrogen is depleted and should be the most abundant. But yeah, we're still working on that. I don't know if that answered your question, or I just like, okay, okay.
I was wondering if you can spoil some of the results you mentioned in the last slide about the chemical composition.
Wait, well, you don't need a slide actually for that. This is tied to, so the paper that Isabel is coming out with, it's tied to another paper by Chen Xie, who is also a postdoc at Space Telescope, working on a different disk. And we are trying to look for ices in the system. we have basically not seen any ices in these disks. At these evolutionary stages, we might be seeing some very interesting ices thanks to James Webb spectroscopy. And I think that's how much I feel comfortable sharing in something that's going to be recorded on YouTube. I'll tell you afterward.
No questions? Looks like Laura's got a hand up at the back.
Yeah, I have a last question. So you mentioned about this element, ionized element that you do not expect from the corona of A-type stars. What about if it's the end is a binary? Could this explain in some way?
Yeah, actually. So if there is another star that has a corona, that it's there, then yeah. But it would be very unlikely. We have so much spectra of this star. It is very unlikely that if there is a binary, well, it's for sure not a spectroscopic binary. So we don't really know whether it could be hiding there. Another explanation for the presence of a corona that I know it's been explored, it's the fact that these stars rotate so fast, like hundreds of kilometers per second, that maybe they are creating a convective zone just from the differential rotation from the pole to the equator. And so maybe you're creating a convective zone, and maybe that's creating a corona, and maybe that's creating the ionized argon. But there's a lot of maybes there, and yeah, a lot of research that has to happen.
So go on, I'll let you know.
Sorry, I missed the beginning of the talk. I was wondering if there is any chance you can see this, the central star in the ultraviolet, or is it too much obscured by dust? I'm just saying to check for stellar activity.
Yeah, so we don't have any evidence of stellar activity. We do have a lot of spectra from Hubble. And we, yeah, as far as we know, there is, but yeah, true. There is a weird kind of X-ray detection that is not clear it's associated to the star. So that's also where the binary thing would fit. Like if you have an M star or something that it's creating the X-rays, but then you would probably see that in the spectrum. So yeah.
Yeah, it's interesting that the binary scenario is still even debated. Yeah,
but there's so many things that just don't add up.
Yeah. So on the point of things that don't add up, how confident is the Argon 2 detection? How confident is the?
Oh, I don't remember, but enough sigma to that we believe it.
Sorry, how confident is the identification?
Of Argon 2?
Yeah.
I would say, yeah, this end, like we did spend a lot of time trying to look for other species that would emit there because there's emission. Yeah, no, and we got to the argon because it's something that you can see in protoplanetary disks sometimes. But again, much denser environments. But yeah, no, we're pretty sure it's argon.
Okay. Interesting. Any sort of final comments, either on Zoom or in the room? Well, if not, let's thank Isabel again for a fantastic seminar.